Ladies and gentlemen, welcome to the Hong Kong IE Civil Division event, technical webinar on boosting energy harvesting efficiency through novel tri-hybrid multi-stable vibration-based energy harvesting techniques, mechanical designs and potential applications, organized by the Hong Kong IE Civil Division and the Polytechnic University. I'm the MC of today's webinar. We are honored to have Dr. S.K. Lai, who is currently an associate professor in the Department of Civil and Environmental Engineering at PolyU Hong Kong, and is the program leader of the uh, Bachelor in Structural and Fire Safety Engineering. His research interests cover energy harvesting, structural dynamics, acoustic metamaterials, and computational mechanics. Without further ado, I would like to invite Dr. S.K. Lai to deliver the talk. Dr. Lai, please.
Okay, thank you very much, Fiona. Can you hear my voice? Hello,
Yes.
Fiona, can you hear my
Yes,
voice?
yes.
Okay, thank you very much. This is S.K. Lai from the CE department from the Hong Kong Polytechnic University. Today I will give a talk to present our research works. Before talking about this one, I would like to take this chance to introduce our departments. I will spend about 5 to 10 minutes to introduce our departments. The full names of our department is Departments of Civil and Environmental Engineering. This is one of the research academic departments at PolyU. In our departments, we enjoy the high reputations in global recognitions. We have 28 CE scholars vendors on the world's top 2% scientists. In terms of CE global rankings, we are in terms of civil engineering, we are the #1 in Hong Kong, and we are the #1 in Hong Kong, and also we rank #14 in civil engineering according to the QS ranking. According to the Shanghai Rankings global rankings of academic subjects, we rank #3 in civil engineering, #2 in transportation science and technology, and 47 in environmental science and engineering. For our CE faculty highlights, we have 1 member of the Chinese Academy of Science, 7 Changjiang scholars, 1 fellow of the Australian Academies of Engineering and Technology, and 1 fellow of Royal Academies of Engineering in the UK. In terms of academic research, we have high excellence in these aspects. In the past few years, we made significant efforts in research. We awarded a number of research projects from the theme-based research scheme. This is one of the largest research schemes in Hong Kong. The major objective of this scheme is to connect academic efforts to bring long-term developments in Hong Kong. The principal coordinators of these projects are Professor J.G. Tan, our president, Professor S.D. Lee, our faculty dean, Professor Tao Wong, and Professor Y.Q. Lee. The research topics of these 4 projects covers sustainable marine infrastructure, air pollution studies, climate change, and also the typhoon-induced vibrations effects on high-rise buildings. According to these 4 projects, the total amount of the research funding is up to 180 million Hong Kong dollars. In addition to this funding scheme, our colleagues also awarded a number of large funding supports from different sources, such as the Green Tech Fund, Land Conservation Fund, and also we have obtained the RGC projects such as the CRF projects, Collaborative Research Fund, Research Impact Fund. In our departments, we offer the undergraduate program. This is a scheme program and what we call the civil engineering and sustainable developments. For year 1, this is a common year. After year 1, students can select their major studies. We have 4 programs. The first one is civil engineering. The second one is civil engineering in smart mobility. And the third one is the structural and fire safety engineering. And the last one is environmental engineering and sustainable developments. In addition to these 4 programs, we still have 1 top degree program, so we call it environmental and occupational safety and health. For the top postgraduate programs, we have 2 master programs. In addition to these top programs, we have to provide research on postgraduate programs, MPhil degree programs, and PhD degree programs. Departments, this is one of the foundations departments at PolyU. We have a long history of over 50 years. Over the past few years, we have many remarkable and outstanding alumni working in different areas. With their kind support and general health, we have promising developments in these departments. In terms of our facilities, we have more than 30 laboratories, 2 workshops, and 1 research center to support academics, teachings, and research activities. In addition to that, we have 2 national research centers, one for the rail transit, electrifications and automations research technology, and one for steel constructions. Okay, if you are interested in our developments, please visit our websites, our CE newsletters, and different social media channels. We will update our information and latest news regularly. Okay, this is the brief introductions of our departments. Now, let us go back to my talk today. Okay, in this talk, I want to introduce our major works about the energy harvesting and how to make use of the vibrations energy harvesting to harness sufficient energies. In this study, I could not go through too much details on the mathematical formulas. I just want to describe the mechanical designs and its potential applications. In this study, I will introduce 4 major devices we did and we proposed it in the past few years since 2019. Okay, we know that in order to upgrade our qualities of life by providing better transportations, government services, and also infrastructures. Due to the urban developments, we need to have a better understanding how to develop a smart city. In order to do so, we need to enhance our sustainability and working efficiency. Through the developments, we also want to maintain minimum impacts to our environments. To develop livable and resilient smart cities, we want to we know that the applications of IoT devices it is very important in the development of smart cities. Reference to this figure, we know that there is an potential increase of using IoT devices to support our to enhance our life quality. So, and how to support those IoT devices? One of the major issues is how to provide an autonomous and continuous power supplies to support those devices. For those, most of them, they are just low power sensors or low power devices. Okay, our focus is on vibrations energy harvesting. In this one, vibration energy harvesting is similar to other types of energy, renewable energy, such as solar energy or wind energies. The concept is very simple. We just convert mechanical energies into electrical energies. Okay, we all know that the basic principle, but how to realize this one, this is a technical challenge. And why it is so important is because we want to explore our educations in every aspect in our society. So that's why with the presence of these systems, we are able to increase the versatilities and the flexibilities of using IoT devices in different areas, especially those remote areas where the access of power sources is impractical or limited. So that's why with the user with the presence of these technologies, we are able to explore the deployments of sensors and devices in everywhere in our city. So that's how we can realize the concepts of smart cities in everywhere. Okay, we know that vibrations are omnipresent in different aspects, such as civil structures, vehicles, transportations, railway tracks, and oceans wave. When we did simple reviews in the past few years, we observed that since 2010, there is a substantial increase. There has been a substantial increase of vibrations-related energy harvesting research. Recently, the numbers of papers is maintained at about 600 papers per each year. So that's this in this direction, it is highly competitive. What as I mentioned before, the concept is very simple. Okay, we just convert mechanical vibrations energies to electrical energy. What is the technical challenge? Because we found that the ambient conditions, no matter on vehicle transportation, civil structures, they are under no frequency, low amplitudes, and time variance and random nature. Okay, we cannot control the vibrations frequency and vibrations amplitudes. If we want to design a universal system, we need to think about how to design suitable or applicable systems to harness sufficient energy. So that's their two major issues. The first one is that how to enhance the efficiencies in terms of conversions efficiency. And the second one is how to generate a sufficient power supply. When you take a look on this table, we found that I just list out some typical examples here. The frequency and the excitations amplitudes, they are at under low levels. Okay, in our study, we consider two aspects. The first one is that we consider that how to harness energies. There are different types of energy harvesting mechanisms. For example, we may use an electromagnetic generator, triboelectric generator, and the piezoelectric generator. Okay, they have their own advantages and disadvantages. But how to combine all these generators into a single hub or into a single system that can help us to extract all advantages for this working mechanism. This is our targets. For example, electronic magnetic generator, it can produce higher current outputs, but the power output, voltage output is still low. For the triboelectric Leno generator, since the dimensions of this generator in 2012, we know that the voltage supply is high, but the output current is low. So we want to extract different types of energy efficiencies and advantages for this working mechanisms. This is our first goal. The rationales we can integrate different transduction mechanisms together is that to adjust the problems under low frequency, low amplitudes, and time variance approach. We consider that the use of the piezoelectric materials, because it has a higher lateral vibrations frequency through the presence of piezoelectric materials, we are able to enhance the system, our desired system for up conversions approach. The second one is that low frequency energy harvesters, we require a large pool mass. And when we use this large pool mass, we can design an electromagnetic generator inside the system. And as I told before, both piezoelectric and the triboelectric approaches, it can produce high voltage outputs, but electromagnetic approach, it is more suitable for large current application. So that's when we consider the electrical performance, we could combine all these three types together, similar to this figure. Okay, we have EMG, PEG. PEG is the piezoelectric approach, and we have the triboelectric approach, and then we combine it into a hybrid generator to enhance and push the working efficiency. The second one is that in addition to design a system with different types of working mechanisms, we also make use of the nonlinear multi-stable approach to do that. In the past, we know that Western's effects is a common approach. We can absorb energies under these conditions. But the problem is that we cannot control the excitation frequencies because this is time variance and random in nature. So that's why we want to explore or expand the working mechanism or the working bandwidth of energy harvesters in energy absorptions. So let us take a look on a simple diagram here. If we design a system, just a linear approach, the bandwidth is very narrowed because we can only absorb energies under a Western state. If we design a nonlinear system, we can explore the bandwidth to a wider frequency approach. So that we want to incorporate the use of the nonlinear approach to do that. In terms of the nonlinear systems, we can design a monostable system. Monostable, it means that we just have only one stable state. We can also design a bistable or tristable states. It depends on what we want to design. When we increase the numbers of stable states in our nonlinear system, the design could be more complicated. But the problem is that we can reduce the potential barriers to excite the system more easily. For example, the monostable state, it is very easy to design this system, but the problem is that it is still the working bandwidth is still limited, so that's why it is unable to perform well in real applications. In this study, I will demonstrate how we can achieve different stable states to achieve better results. Okay, how to design a multi-stable nonlinearity system? Okay, I list two examples here. For the type A, when we have a cantilever beam at the tip of this cantilever beam, when we attach a moving mass, okay, with respect to this system mass, we can design and we can optimize the parameters HA. HA is the separation distance between these two magnets, and dA is the dimensions of this magnet, system magnets. When we change the parameters HA and dA, we are able to achieve monostable, bistable, and tristable states under different parameters values. And for type B, we can still achieve this one by adjusting the parameters HB and DB, okay? It depends on the system. This is a simple example to show us that how we can achieve a nonlinear system and how we can adjust the systems to achieve our desired approach. Our focus, we want to use a single approach or the same setting configurations that can be applied in multiple applications. For example, for mechanical vibrations energies, for human biomechanical engineering, and for blue energies to extract energies from wave motions. We want to achieve this one, and we don't want to change the configurations. We just want to use a single design that can achieve different potential applications. This is our major targets in this study. Okay, in this verse, I will introduce four design models. The first one is the structurable stable nonlinearity enhanced hybrid energy harvester. The second one is we adopted the magnetic levitation design. And the third one is that we use the core stable hybrid energy harvester design. Core stable, it means that there are 4 stable states. And the final one is that this is our reasons work we completed in the last year. This is the red pinion steering speed amplified approach. I will show the performance of each one and compare the performance to show that how we can enhance the working performance. And focusing on what I presented before is that we focus on the ambient conditions excitations, no frequency within the range 1 to 15 Hertz, no amplitude 0.5 to 2 G. G is the gravitational effects, and time variance and random nature. I will use the human motions to demonstrate how the energies can still be workable under the random motions. Okay, let us go to the first one. The first one is the searchable, stable, non-linearity enhanced tri-hybrid energy harvester. This is a U-shaped devices configurations. In this one, we design the piezoelectric beams on both ends, and we have a moving slider. And under the motions of this moving slider, it can form an EMG, electromagnetic generator. And we still use the piezoelectric triboelectric materials. So that's when we add them together, we can form a hybridized approach. This is the assembly procedures, how we can formulate these U-shaped devices. Why this is a searchable stable state? Because when we take a look on this diagram, we observe that we can achieve 7 stable positions. This is the first one at the center of the system, and then this is the second stable state. This is the third one, 4, 5, 6, and 7. This is the only one I found it in the literature that we can achieve this higher stable states to design such a nonlinear system. And according to this diagram, you can see that there are 7 stable states. Why we want to design this one? Because we want to reduce the potential barriers so that the system can be excited easily under given excitation conditions. Okay, this is the top one. In this figure, the top one, this is the variations of the electromagnetic fields under the motions of this moving slider. And the bottom one and the bottom figure, it is used to show the variations of this moving slider with respect to the triboelectric effects. The dimensions of this system is not so large. Okay, the top one is just 15 millimeter. The length is 63 millimeter, and the height of this supporting beam is just 47 millimeter. We want to design a lighter and smaller devices that can apply in different potential applications. And the rate of this system is just 85 grams. Okay, I just want to present the test results because we focus on the frequency range from 2 to 12 hertz. So that's under different accelerations, 0.5 G up to 1.5 G, you can see the variations. When you take a look on this one, there is a certain drop in terms of the open circuit voltage, because this is because the presence of frictional damping effects in the system. So that there is a certain drop, but in general, we can provide an average results in terms of different accelerations effects. And also, we also studied the behavior of individual units. GBA and GBB, they are piezoelectric units, and EMG is the electromagnetic approach, and TEMG is the triboelectric nano generator. When we compare each one, we studied the behavior of the power supply and the voltage supply. Okay, and we also care about the hybridized effects. Okay, the overall performance of this device. The maximum power is 24.2 milliwatts. This is the peak power, maximum power we can generate. Okay, because the individual units could generate the AC power, so that in order to make the electronic circuits more easily, we decided a system to connect them in parallel, and then we use the rectifiers to convert the AC powers to DC power. So that's why we can directly connect this to a storage or electrical device. There are different applications for this device. We can use this to activate an accelerometer. We can use this to power up LED lights. And even we can use it to operate the temperature devices. Okay, here I want to show some videos. In this slide, in this video, we have the accelerometer. When we use the human motions under the effects, under the power supply of this one, we can operate this accelerometer. And the other one is that we want to power up these 5 electronic devices under 1G. G is the accelerations effects, and the lower frequency hertz is 8 hertz. Okay, let us take a look on that. Actually, we can operate more devices under the operations of this device. I just make use of 5 electronic devices to show this efficiency. As I told before, we also use this to demonstrate whether we can use this tri-hybrid energy harvesters to absorb human motions energies. We can do that. In this one, we did some experimental studies using the handshaking motions. And also we attach this device in horizontal device and or in vertical alignments under the walking motions and the slow running motions. And you can see that the performance of the horizontal alignments and the vertical alignments, they are different, but the results is still okay. Okay, let's take a look on this one. This is the electronic device we want to power up under a slow motion, running motion. We can power up this this electronic device. Okay, after that, we compare the electrical performance of our device with respect to other similar devices. You can see that our range can the bandwidth of our device is workable under 2 to 12.5 hertz. This range. Under the operating conditions 5 hertz and 1G, the peak power supply is 24.16. This is larger than other similar devices. And the power densities, we push it up to 700.3 watts per meter cube. You can see that this is higher than the others. The second one is that the tri-stable hybrid energy harvester based on magnetic levitations. In this one, we don't want to focus on the power supply because we just want to see how we can make use of the different types of magnetic arrangement. We are able to change the nonlinear behavior of the system. Okay, in this one, we just consider the use of the electromagnetic approach and also the triboelectric approach in this system. We have the nonlinear behavior of this system. We can achieve the tri-stable state. You can see that when the moving magnet is moving in this way to the left-hand side or the right-hand side, we can achieve 3 different equilibrium positions. Okay, now how to consider these effects? We have a moving magnet, and then there are two numbers of 6 fixed magnets. 2 of them we put it on both ends, and we still have 4 magnets surrounding this moving magnets. With the this arrangement, we can achieve different stable states from monostable to tri-stable approach. We just adjust 2 parameters. One is the distance, the separation distance between these 2 magnets, and the second one is the magnets is the center of this moving magnets to this fixed magnet surrounding this one. Okay, you can see that when we set different types of parameters here, we can achieve, according to the bifurcation diagrams, we can achieve the results from monostable to tri-stable, and then the nonlinear system can go back to the bistable state when we increase the parameter D from 15 millimeters up to 18 millimeter. D is the direct distance between these two magnets. Okay, and RB, we set 3 different scenarios. The first one is 10 millimeter, the second one is 11.5 millimeter, and the last one is 16 millimeter. So that when we look at these figures, we see that these two unstable points, when we increase the effects, RB, the values of RB, it could they appear or subtle locked points could disappear in this situation. So that we want to based on this theoretical analysis, we can determine what parameters we can use it in this design. And this is the events we achieved the tri-stable states. We still need to consider these two cases. We can compare these two cases. For the first one, we consider RB is equals to 10 millimeter and D is 53.5 millimeter. And the second case is 11.5 millimeter and D is 58.5 millimeter. We can compare when we consider this figure. The second case with lower potential barrier. Okay, when we compare the first one. So that we select these parameters to design our system. Why we call this is the symmetric approach, because this is just horizontal alignments. We do not need to consider the effect of gravity. When we put it as in terms of the vertical alignments, when it could generate an asymmetric system. It means that we still need to consider the effect of gravity, Fg here. In this case, similarly, we can still observe monostable state, bistable state, and tri-stable state if we change the parameters D and RB. Okay, we did 2 experiments to study different alignments, horizontal alignments, and also the vertical alignments in our study. Okay, you can see that our focus is from 3 Hz up to 8 Hz. Under different excitations amplitudes, it is still good under these effects. And in the other case, we studied the efficiency of monostable state. How to achieve this monostable state? It is so simple. We just need to remove all these 4 magnets. Okay, without the provisions of these 4 magnets, B1, B2, B3, and B4, we can achieve the monostable state. And in terms of when we put it as horizontal directions, the maximum power supply is 6.9 milliwatts. Okay, you can see that the EMG contribute higher power supplies as compared to the triboelectric approach. But when you consider the voltage supply, the voltage supply of the triboelectric approach is much higher than that of the electromagnetic approach. Okay, this is the video to show the effects under 1G. Okay, we can easily excite and operate these 3 devices. Okay, the second one is when we put it into vertical directions, we can observe similar results. And the maximum power in vertical alignment is 6.4 milliwatts. This is the video to demonstrate the efficiencies of the device. Okay, now when we compare similar approaches, we see that we can reduce the vibrations amplitudes, and also we can extend the frequency range from 3 to 8 Hz, and the maximum power is 6.9 milliwatts. In terms of the power density, it is up to 132 watts per meter cube. When you compare this value with respect to the previous design, our first design, the result is less than that. But because in this, as I mentioned before, we want to study how to make different combinations of the magnetic approach. We are able to design different types of nonlinear systems. And the last two device is this one, the ultra low frequency. This device can be workable under 1 Hz. Okay, in this design, this is the schematic to show the internal components of each one. We combine 3 different approaches together, and the dimensions of this one is just they are just 70 times 25 times 18 millimeter cube. Okay, in this one, learning from the previous design, the magnetic-based approach, when we make use of different combinations of magnetic array, we can achieve tri-stable approach and the cross-stable approach. When we put it into our vertical alignment, this is a tri-stable state. Why we call this as tri-stable? When you refer to this potential energy diagram, you can see that they are 3 stable states. When we put it into horizontal alignment, we can achieve 4 stable states. So that this is what we call the cross-stable states. And when we just pick up these two modes for our analysis, the cross-stable mode and the tri-stable mode, the working range of the cross-stable mode is more efficient than the tri-stable mode because you can compare the working efficiency. The working efficiency in terms of the frequency bandwidth, this one is wider than the tri-stable mode. And this figure shows the all the components we use it to combine the whole system. In terms of this one, you can see that the PEG and EMG, they contribute more in terms of the powers to volume ratio. The 10, because we combine 2 different approaches in terms of the triboelectric approach. One is the freestanding approach, and the other one is the contact separations approach. When you consider this, the triboelectric approach, the efficiency and the power ratio is less than PEG and EMG. But in terms of the mechanical design, we need to have this triboelectric effects because it can enhance the durability of the system. We also compare the electrical performance in each individual units to show under different tri-stable and cross-stable state. And the standardized power density of this device is about 3.7 milliwatts per cm cube per G square. And what does it mean? It can generate the peak powers of 86 milliwatts. It means that if we want to power up sensor level with 400 milliwatts, it can supply powers to charge it for 12.9 seconds. Okay, let us take a look on this one. What is the working efficiency of using this device? You can see that under slow motions of shaking motions, okay, we can operate all these 12 electronic devices at the same time. And how about the human body motions? This is under the high frequency motions. We can operate more than 300 LED lights. And this one, we put it on the wrist, okay? Under large amplitudes but low frequency effects, we can operate all these 3 electronic devices at the same time without any problem. Okay, we also did a comparisons between our current designs and with respect to our cerebral designs. The power densities can be the power density. Let's take a look at this one. The power density can be enhanced from 1.97 milliwatts per cm cube per G square up to 3.7. Okay, almost 1.8 times when we compare this one. And the working frequency we turn down to 3 hertz instead of 5 hertz. Okay, the last one is we proposed this device in the last year. In the end of the last year, this is the queen-stable speed amplifications approach. What is the queen-stable? It means that when we design a system, a nonlinear system that has 5 stable states. In order to further enhance the working efficiency, we did a simple mechanical designs by using the red pinion steering system. Okay, you can see that there is a red and pinion system here. with respect to this one, you can see that when the moving magnet is moving to these positions, to the left positions, the magnets are raised on the top and at the bottom, they could move to the opposite position so that at the same time, we can generate double power. And according to this one, we design a system with 5 stable states from 1 to 5, and this is the potential energies approach. We did nonlinear analysis under different excitations levels. For example, from 0.5 G up to 1.5 G, the working bandwidth can be up to 1 Hertz up to 12 Hertz. And the standardized power density can be up to 7.7 milliwatts per cm cube per G squared. And we also did a comparisons. What I want to show in this figure is that when you compare the hybridized approach with respect to individual units, the charging voltage of the hybridized approach is better than the individual units, okay? Is the red curve. And using this one, we put it on, we tested this one using different human motions, such as we just put it on the side pockets, and pads, trousers pockets, and under different human body positions, we can generate supply parts to operate the system. And how about the durabilities of this system? After we tested for more than 40,000 cycles, you can see that when you refer to these two figures, there is no any deteriorations in terms of the voltage performance. Okay, and let's take a look on this video. Oh, sorry. Let's take a look on this video about how to make use of this one. We just put this device inside the pockets. And then we want to operate this GPS sensor under slow running motion. Okay, after 5 minutes, we can turn on this GPS device to locate the positions of this person. Okay, when I showed the videos before, you may ask questions that it just uses to operate low power or low levels devices or sensors such as LED lights or accelerometers, a low power accelerometer. How about can we use this to operate a higher power device? Okay, this video shows that we can use it under the low frequency conditions to operate a smartphone, to charge a smartphone. Under the operations of this device, when we turn on the power, sorry. When we turn on the connections, you can see that we can directly charge up this smartphone. This is a periodic and regular motion. How about if we use the body motion, biomechanical motion? When we use the handshaking motions, we can still operate and charge up our smartphone. We can regard a smartphone as a small-scale computer. Now we also use it to absorb wave motions energy, okay, not just vibrations energy. When we put it into a floating body, let's take a look what could happen. when we put this our prototype into a floating body, and then we put it on the wave motions. We want to operate the GPS sensor. After about 15 minutes, we can operate the GPS sensor. The vibrations frequencies of these wave motions is under a very low level, maybe just 1 to 2 hertz. So now we turn on the sensor. Okay, now in this talk, I presented 4 different types of models for energy harvesting, for vibration-based energy harvesting. They have their own disadvantages, and our major target is that we want to enhance the working efficiency, explore the working bandwidth, and increase the peak power outputs. For the first type, we can only achieve the peak power output at above 24 milliwatts. But in the last year, we just achieved the new system that can approach the peak power output up to 800 milliwatts. And when you compare the peak voltage, when we remove the piezoelectric approach, the peak voltage is just about 40 watts. And if we install or incorporate the use of the piezoelectric approach, we can achieve the voltage, the peak voltage output up to 80 watts. So that in the future, we will also optimize this design so that using the same setting configurations, we are able to apply it to different potential applications. Okay, now, at the end of the day, we design systems for low frequency, low amplitudes, and time variance natures. We use 2 different design approaches. The first one is the nonlinearity enhanced mechanisms. In my talk, I presented we can achieve different stable states from bistable up to susceptible stable states. And also, we need to have some appropriate mechanical designs, such as using levitations, fan-folded structures, and the red pinion steering system. And we want to use the same setting configurations to that can work in different potential applications. For example, biomechanical energies, structural vibrations energies, and wave motions. Okay. Last but not least, I would like to sincerely thank the financial supports for this work from the National Natural Science Foundations of China, Research Grants Councils of Hong Kong, Hong Kong PolyU, and the Chinese National Rail Transit Electrification and Automation Energy Technology Research Center. They provide general financial supports to this research. And lastly, I would like to thank my teammates and my students who made significant efforts in this research. Okay, thank you.
Thank you, Dr. Lai. We will now proceed to the Q&A session. Please feel free to leave a message to the chat room if you have any question regarding the webinar.
Okay, any questions about this research? Well, Fiona, do you have any questions about the talk?
There's no question, then we may directly go to end today's webinar. So thank you, Dr. Lai, as the speaker of today. We have prepared carbon credit certificates for you as a token of thanks. I'm sure all of us have learned a lot tonight and hope you have enjoyed the webinar. The digital attendance certificate will be sent to your email in 4 weeks. Once again, thank you very much for joining the webinar, and we wish you all a good evening. See you all again in future events.
Okay,
Goodbye.
bye bye.